All right, welcome everyone. For today's prep, we're going to look at two other types of line integrals. So let's just remember back when we first started looking at these line integrals. The setup here was that we had a curve sitting on the xy plane, and then we have a function f of xy, which is giving us kind of the height above the curve. And so when we think of this, we end up with all the points certain height above our curve, sitting above our curve, and we end up with this ribbon shape. And the area problem that we considered was, well, how do we find the area of this ribbon where it goes from the curve C sitting on the xy plane and extends up until that surface? So we have the kind of the top of our curve here sitting on the surface. And the question was, how do we find the area? And the answer to that was the line integral. And that's what we saw how to calculate. Well, now we're going to look at two other line integrals. And the way we can kind of think of them is kind of standing off to the side here and looking at, let's stand off parallel to the y-axis, and let's look at kind of the side view of what's going on from that y-axis side. So we're going to imagine kind of taking this ribbon shape and flattening it down onto the YZ plane. So we're going to, all these little curves, we're just going to fold this thing, flatten it down. And then we're going to do the same thing over here. We're going to imagine standing alongside the x-axis, and we're going to kind of look from that side. And what we're going to do is we're just going to, again, squish that ribbon down onto the XZ plane. And this is going to give us two new types of line integrals. One with respect to x and one with respect to y. All right, so let's get to the definitions here. Scroll through all the stuff we've done already. All right, so some more line integrals. All right, so the line integral we've already looked at was this line integral over curve C of the function f of xy, and the differential here is ds. That's with respect to arc length. So that was involving our arc length differential. Now the two new ones are going to be the line integral of the function with respect to x and the line integral with respect to y. So we have the dx here when we're doing it with respect to x, and yeah. All right, so this line integral, this first line integral here, this is going to be the projection. So we're going to look at the projection of the ribbon onto, and in the case of the x integral, we're going to project it onto the xz plane. And for the y integral, we're going to project it onto the yz plane. So you can kind of imagine the curve being squished down onto either the x-axis or the y-axis here. So we're projecting that ribbon onto either the xz plane or the yz plane. All right, so how does this look? So what is an example of how this would look? Well, let's consider the case of with respect to x. So we're going to have our z-axis pointing up, and then the x-axis will be flat. And let's suppose that, again, we're going to squish down this ribbon. So let's suppose that we get something like this. We have the start right here, and then our ribbon, when we squish it down, we get one fold. So our curve, again, our curve C, the original curve, is sitting on the xy plane here. And what we're looking at is the ribbon that sits above it. And so there's a little bit of overlap. So we have this section here that we've kind of folded back on itself. All right. Well, also with a curve, there's a stop and there's a start point and an ending point. And so when I said this, I said we were starting here and we were going to kind of travel along our curve. Now, technically, our curve is on the xy plane, but we can view the top of our curve here. And we're going to go from this side, our starting point, to our ending point. So there's a directionality when we talk about curves. So let's suppose this is the direction that we're traveling in. So what this line integral with respect to x does is, again, we collapse the ribbon down onto the xz plane. And then what this line integral calculates is the net area that we see. So it's the area when we are traveling to the right minus the area. So we have this, we're traveling to the right here. So we're calculating the area of this region. But then we're subtracting out any area where we're traveling to the left. So it's the area to the right minus the area to the left. So we collapse the ribbon down onto the xz plane, and then we have certain sections, our curve is moving to the right, and then certain sections, when we fold, it's moving to the left. And what we do is we calculate the area for the view that we see when we're moving to the right, and then we subtract out any sections when we were moving to the left. And that's the what these line integrals do in terms of x and y. Now, how we actually calculate these is we're going to calculate them very similar to how we did it with our regular line integral with respect to ds. Now, the only difference here is our differentials aren't as nasty. So the dx here is just x prime times dt. And let's just remember, we're still going to have to parameterize the curve in order to calculate these. So we're still going to parameterize curve C. We're going to let x equal to a parametric equation. We'll call it x of t. We'll let y equal a parametric equation, y of t. And then we'll still have some interval for t, some starting time and some ending time here. And so dx, the differential dx, is just the derivative of our x equation times dt. And then the differential dy is just the derivative of our y equation times dt. And then we just fill in the pieces of our parametric curve, x of t and y of t. And we integrate, as usual with respect to t here. And normally, as kind of a notational thing, when we have a few of these line integrals put together, so our notation is, say we had the line integral of some function p of xy over curve C with respect to x, and then we had another line integral of some other function q of xy with respect to y over that same curve C. Well, the standard way to write this is to kind of combine the integral sign and to write this as the line integral over curve C of p of xy dx plus q of xy dy. So this is a notational thing for how we usually write the sum of these two line integrals, where we have a line integral with respect to x and a line integral with respect to y, and the actual curve there is the same. All right. So we just consolidate things and have one integral sign, basically. All right, let's try an example. So let's look at this line integral of y squared dx plus x dy, where we're going over curve C. And in this case, I think we're going to do part A. We're going to start with part A here. So in this case, curve C is the line segment going from the point -5, -3 to the point 0, 2. All right, so as with any line integral, first thing we need to do is get the parameterization for our curve. So we got to parameterize C. All right, so what's our standard? We're dealing with a line segment here. So what's our standard parameterization? Well, this is something we looked at way back. We have our vector representation for a line segment. So the vector function r of t is 1 minus t times the starting position plus t times the ending position vector. And t goes between 0 and 1 when we use this parameterization. So let's actually kind of fill this out. So this means r of t, if we kind of fill in our points here, our starting point, we want to go from -5, -3, so that's going to be our starting point. So -5, -3. And then our ending point is 0, 0, 2. So we're going to have plus t times 0, 2. And this is fine for a vector equation, but let's actually write out what the parametric equations are. So x, if we kind of follow along, the equation for x here is going to be -5 times 1 minus t, and then 0 times t. So our x equation is going to be -5 plus 5t. And then what about our y equation? What's our y equation going to be? Well, it's going to be -3 times all of this, and then plus 2t. So when we write that out and simplify, we end up with -3 plus 5t. Yeah. All right. And our parameter t here is going from 0 to 1. So we have our x equation, our y equation, and we have the interval for t. So now we're ready to actually set up our line integral. So that's the next step, is we're going to substitute everything in. So what was our line integral here? We're doing the line integral of curve C, y squared dx plus x dy. Let's write out what all of this is. So first of all, we're basically converting this into a definite integral. So that's what this kind of substitution step is we're just getting it into a definite integral. So our limits for t are going from 0 to 1. All right, well, let's fill in what y is. So y is -3 plus 5t. And then we have our dx here. So we got to calculate dx. So let's do that. So dx, the differential, is just the derivative of this. So 5 times dt. So we're going to have a, not -5, +5 dt. And then, so that was our dx. And then we go to the next part, the x dy here, and we do the same kind of conversion. So we want to convert the x term that we see. So x in this case is -5 plus 5t. So we're going to have plus -5 plus 5t. So that's our x value. And then we also have to calculate dy. So what is dy? Well, we just differentiate our y equation here. We get 5. And then we throw on a dt. So when we convert that, the dy becomes 5 times dt. So again, when we plug everything in, the y term that we saw right here, we plugged in the -3 plus 5t. And you know what? I'm missing the squared here. We need that squared. So there should be a squared up here. Then the dx that we calculated, we threw in right next to it because we had the dx. Then in the second part, we had our x value. So we figured out our x value and threw that in. So -5 plus 5t from our parameterization. And then we also calculated dy and put that right next door. All right, so now the goal is to just simplify this down and evaluate it. So the first item of business is just, now these two differentials are just, we don't need both of them anymore. So we can just consolidate this into one single definite integral. So we end up with the integral, well, what do we get? There's a 5 in both of these. So let's factor out a 5. Maybe put that in front. Then we'll have the integral from 0 to 1. And then let's multiply out this negative 3 plus 5t squared. So when we do that, we get 9 minus 30t plus 25t squared. And then we have our negative 5 plus 5t term still being added in, dt. So now we just have 1 dt at the end here. And keep consolidating. So the negative 5 and the 9 give us 4. The positive 5t and the negative 30t give us negative 25t. And then we have the positive 25t squared. And now this is just a regular definite integral. So get the antiderivative and then plug in. So when we do this, the antiderivative is 4t minus 25t squared over 2 plus 25t cubed over 3. And then we evaluate from 0 to 1. And then we just plug in. Top number goes in first, which will give us, powers of 1 are just 1, so that'll be easy. And then when we plug in 0, these are all power functions, so they're all going to be 0. So when we do this, I won't go through the simplifying part, but we end up with negative 5 over 6 if we were to simplify it. All right, so that's the idea. So we'll try another one of these examples in class on Monday. And for the next part of this, same function. So we're doing the same kind of the same function here that we're integrating. We're doing the x line integral of the function y squared, and then the x and then the y line integral of the function x. But now we're going to be looking at a different curve. In this case, we're going to be looking at the curve when it's a parabola given by x equal to 4 minus y squared. So we'll see that in class. All right, so have a nice rest of your day, and we'll see you on Monday. Bye-bye.